Hey guys, in this video I wanted to talk a little bit about energy, and that's going to include potential energy and kinetic energy, and also some non-mechanical energy. Okay, so I've got a graph of v of x here that is the potential energy function as a function of x, and the potential energy is associated with some conservative force, and I'll talk a little bit about conservative and non-conservative forces and just a force in general. But hopefully you should know, Newton's laws, what a force is. Maybe you are familiar with kinetic and potential energy. That would be ideal. Uh, because, it's such an important concept in all of physics, and especially in quantum mechanics too. Um, and so this brief video may not cover everything that you need to know, and I will have links in the description. Again, energy is just such an important topic. Okay, so a potential energy function, we generally like to define them as having an asymptote at x equals 0, right? So is the potential energy goes off to positive or negative infinity, right? This potential energy function is going to be about 0, and I'll explain why we like to have that. So, this shouldn't be as bumpy of a line as I'm making it, but a potential energy function may look something like this. Right? This is very arbitrary. It may not ever represent a real force, but, and this will continue off asymptote at 0, And, so we can now look at what this potential energy function means. So I'm going to first give a few definitions of conservative forces, okay? And we're really just going to be dealing with conservative forces in quantum mechanics. And I'll talk a little bit about non-conservative forces and why we don't deal with non-conservative forces in quantum mechanics. And I'll touch on that at the end of this video. But right now, if I'm talking about forces, I'm just talking about conservative forces. And I will define what conservative forces are too in a minute. But by Newton's second law, we know F equals ma. And F is a vector, vector A, vector, right? And this is not just for conservative force. This is for any force, non-conservative as well. The next equation I'm going to write is just for a conservative force. But just to understand, qualitatively, a force is something that changes the motion of an object. Okay, an object is, has a velocity in this direction, it's moving in this direction. A force can either change its direction or it can speed it up, too. So, next, we can see the relationship between a conservative force and a potential energy function. And only conservative forces have a potential energy function associated with them. But we can define force F. This is a conservative force. I'll have F sub c down here just so you know that this is just a conservative force, and I'm going to leave the vector arrow off. We'll just be dealing with the magnitude, the absolute value. That's going to be the derivative of the potential energy function v of x, and I'll just keep on writing v of x so we don't confuse this v with velocity, which we're also going to talk a little bit about. Sorry, minus the derivative. I'll fix that minus sign there. So it's the negative derivative of the potential energy function with respect to x. Okay? And this is just for conservative forces. And let's look qualitatively. So a force, we're just considering a one-dimensional object right now. This can be generalized to more than one dimension, but just to stick with the easy case for one dimension. And again, you'll also find out in quantum physics that we're really just going to be doing one-dimensional work for a good part of the course, and then we can generalize to 3 dimensions, and it's actually going to be really, really easy to make that generalization. And that is why, to keep things simple, we just work in 1 dimension, and we're going to be doing that for the rest of classical physics too. But this is our last video on classical physics, so yeah. So we consider a particle with positive force, the force is going to be accelerating the object in this direction, towards the right. A negative force is going to be accelerating the object towards the left. Okay, and we can look qualitatively, what does this equation mean for the force? Okay, and I guess could put the vector here. This is just for one dimension, though. For more than one dimension, you need a gradient operator. And this is not super conventionally correct, but you can kind of get the idea. And I'm just including the vector because it can be either positive or negative, just to clarify that. Okay, so say over here, the derivative, right, it's positive slope, like right here. Derivative is positive, which means the force is going to be pointing in the negative direction, right? Because it's negative, the derivative is positive, so the force is going to be pointing in this direction, right? So right here, the force is going to be pointing in this direction. I can fix that arrow. Okay, that direction. Over here, the derivative is negative, right? Negative slope. So the force is going to be pointing in the positive direction. Okay, positive. Over here, right? This is, it's really, really positive right here, so it's going to be high force, but still negative direction. Over here, it's a negative slope, so positive direction. Okay, right here, derivative, or force is pointing this way. Right here, force is pointing this way. Okay, and you may notice something really interesting. The force is trying to get the object to an area with lower potential energy and getting it away from a place with higher potential energy, right? Right here, the force is pointing this way. So the particle wants to be here, here, here. Particle doesn't want to be here or here. And if it's here, very unstable, right? And we can define different types of equilibrium here. So we have a stable equilibrium where the particle is where it wants to be. There's no force, zero force, right? And equilibrium is always where there's zero force acting on the particle. But a stable equilibrium, you know, if it moves a little bit, it's just going to go back to where it is. An unstable equilibrium, like right here, particle moves a little bit, it's going to try to get farther and farther away, right? No force right here, but just a tiny bit to the right or left, tiny bit to the right or left, there will be a force. And finally is a neutral equilibrium, and that's going to be right here, where, you know, this should be a bit straight, you know, and it's for all intents and purposes, maybe it's asymptoting, maybe it's not quite at a zero potential energy, but for all intents and purposes, it's flat at zero, right? So a little bit over, well, there may be a little bit of force trying to get it away, but for the most part, it's pretty still, pretty static. Not a lot of change with the force because the derivative all around is essentially zero. Okay, so now we understand what a potential energy will do to a force. You're going to try to get to a place with low potential energy. And now we can also say one more thing about a conservative force, which is a conservative force, by definition, obeys the law of the conservation of mechanical energy. Okay, and this is not the conservation of energy. On a quantum scale, it is, and that's what we're going to talk about a little later this video. But for a classical system, conservation of energy and the conservation of mechanical energy, is different. But the conservation of mechanical energy states that the change in kinetic energy plus the change in potential energy, V, is equal to zero, right? That's saying that the change in mechanical energy is equal to zero. Mechanical energy, right, just do ME is equal to the kinetic energy plus the potential energy, and I'll talk a little bit about what kinetic energy and potential energy are. No, yeah, see, kinetic energy is a T. Sometimes people will say KE, but I'm just going to stick with the T and V convention. And this is also equivalent to stating that the change delta of the mechanical energy. And you should just know delta, capital delta, the Greek letter, is always going to, well, not always, but mostly going to represent the change in something. Delta change in mechanical energy is equal to 0. Right, so that means if something has X mechanical energy, it's always going to, at every time, it's always going to have X mechanical energy. And that's for a closed system, right, where there are no non-conservative forces. This is just for conservative forces. And if there's a non-conservative force around, that can actually take different forms of energy, such as heat or radiation, and turn it into mechanical energy, or it could take mechanical energy and turn it into heat or radiation or another form of non-mechanical energy, sort of like friction does. Friction is non-conservative because it takes mechanical energy, and when it slows down the object, it doesn't give it potential energy, right? The object loses kinetic energy. As you'll see, kinetic energy has to do with the velocity, the speed of an object. Both the velocity and the speed is the square of the velocity, which is the same as the square of the speed, because both are scalar, neither are vectors. The square of a vector is a vector. Hopefully you know that. Or the square of a vector is a scalar, sorry. And a scalar is just an ordinary number. Sorry, misspoke on that one. Right? So in a non-conservative force, something like kinetic energy, the velocity of an object can be slowed down. Velocity squared of the object can be smaller, right? And it doesn't give it potential energy, it gives it heat, right? Friction, if you rub your hands together, you will feel heat, and that's turning mechanical energy, the kinetic energy from the motion of your hands, into heat. Okay, I'm just going to write this equation in one more way, which is going to be the change in kinetic energy is equal to negative change in potential energy, right? And I'm gonna box this one in, just because this is gonna be kind of the more tell-all equation. Even though this is the more general standard form, this is gonna tell us a lot more about our system. Okay, so there's a lot of different derivations of this, not this, but the next point, which is the definition of kinetic energy. I'll change colors for this. But I'm just gonna state it here, right? Kinetic energy is equal to T equals 1/2 times mv squared. And this has dimensions of energy, units of joules. You can check this out. You know, joule is a kilogram times meter squared per second squared. Velocity squared is meter squared per second squared. Mass is mass. The dimensions of mass are units of kilograms. This is dimensionally consistent. Should mean, you know, right here you're adding two different energies, right? Remember, potential energy, this function, it is a function of x, but the units are in joules, it is in energy, right? Okay, so you can see what's really important here is not the value of the potential energy. That's very relative. In fact, what matters is the change in potential energy, because we're looking at the dynamics of a system. The dynamics has to do with like the speed, right, and the velocity. So we're just looking to tell us about how the speed of an object changes, right? A force will change the speed, and a change in potential energy will change the speed, because a change in potential energy is a force, right? So this should all kind of make sense tying together. You know, how this equation would go very well with this equation, and as you can see, both of these only apply to conservative forces too. But because we're interested in how the speed of an object changes, right, how the motion of an object changes, we're really concerned with the change in potential energy, right? So if, say, we have a potential energy function like this, right, asymptotes here, some arbitrary function, right? asymptotes back here. Not great drawing, but these are about the same value. Because we're really only concerned about the speed, the change in potential energy, we can really just shift this down here, right? And that's not going to make a difference in our change of potential energy. The difference between here and here is the same, even if you bring the values of this down, right? That should make sense. If you bring it down, it's not going to affect the slope or the change in potential energy. Okay, and so that's why we like to define these potential energy functions to be zero at to asymptote to zero. And that should also make sense that, if a force is around this area, right, when it gets to negative infinity, infinity, it's going to flatten out. The force isn't going to have a lot of impact. Gravity, potential energy function of gravity looks that's bad axis. Looks something like this. Can't draw straight lines today, huh? It's going to look something like that, right? Go down, and it should be symmetric, but it's sort of the equation. It's the potential energy V sub G, right, of X, or it's actually going to be of R, but that's like the spatial dimension, the radius of an object away from the Earth's surface. It's going to be equal to the negative G m. This is going to be the mass. In the case of Earth, this is going to be the mass of the Earth. This is going to be the gravitational constant. So this is a constant over r squared. So this is just some constant times the function minus 1 over r squared, and that looks sort of like this. And you can graph that, see sort of what it looks like, but that would make more sense because the force as you get closer is greater and greater because the slope increases, and as you get out, there's not a big slope, it flattens out, and it's also symmetric because the Earth really doesn't care what side of it you're on. Theoretically, if the Earth was a perfect sphere, it's not, but if it were, it would be exactly this. There's weird landforms that can change it just by a very, very slight amount, but we consider it to be symmetric just because for all intents and purposes it is. Okay, so that is why we really only care about the change in potential energy. And note that as you change potential energy, if you go to less potential energy, the object's going to speed up even more, and that should make sense. Force is making it speed up, right? So again, I know I've said this a bunch of times, but this should really just make sense to you, that how force and potential energy are related, how potential energy is qualitatively, and how it affects the motion of a particle. That's so crucial to understanding for you to understand quantum mechanics. Okay, so this is the last part of this video. That's about why we only care about conservative forces in quantum mechanics. Okay, and so I said a non-conservative force, it's going to have mechanical energy be transferred with different types of non-mechanical energy, and that can include, I'll change colors. So not mechanical energy. It's mechanical energy, not me. And I've got two really good examples right now that I'm just going to focus on, and this is going to be heat. The second one is going to be radiation. Radiation. not the easiest thing to write up. So radiation. Uh, and the reason that these are not going to be considered in quantum mechanics is that on a microscopic scale, it really is uh, mechanical energy, right? Heat is defined, the heat of a system. So if you have a gas, right, a gas with a bunch of atoms in it, the heat of that gas is the average kinetic energy of all of the particles in that gas. Well, that's not going to exist on a microscopic scale. On a microscopic scale, on a quantum scale, it is kinetic energy. So this is mechanical energy. For quantum mechanics and radiation, you're going to see we're going to talk about the particle called a photon. And these photons, radiation is just the kinetic energy of a photon, right? The kinetic, the kinetic energy of a photon is proportional to the photon's frequency, sorry. And you will see that in our video on the photoelectric effect. But the radiation is the mechanical energy of a light particle, right? And it's not always visible light. It can be a radio wave, but they're all carried by the same particles. You know, the colors of the rainbow, or gamma radiation, or just a wave that you get a television signal from. It's all carried by a photon, and that photon has energy with it, and radiation, we view that energy classically as radiation, but on a quantum scale, it is really just the mechanical energy of the photon.